The cosmos, in its staggering immensity, is a tapestry woven not only with the vibrant threads of visible light and tangible matter, but also with the subtler, often overlooked, strands of silent energy. These are the fundamental forces and phenomena that operate beyond our immediate sensory grasp, yet they are the very bedrock upon which all observable reality is constructed. Think of the unseen gravitational pull that orchestrates the dance of galaxies, or the subtle electromagnetic fields that permeate every inch of space, enabling communication and binding atoms together. These are the silent architects, the invisible engines driving the grand cosmic machinery. Delving deeper into this realm of the imperceptible, we encounter the perplexing yet profound concept of the quantum vacuum. Far from being an empty, inert void, this fundamental substrate of the universe teems with a latent, boundless energy. It is a dynamic arena where particles spontaneously blink into existence and vanish just as quickly, a consequence of inherent energy fluctuations known as zero-point energy. This isn't some theoretical abstraction, it's a tangible manifestation of the universe's restless vitality, a constant effervescence at the very fabric of space-time. Imagine a ceaseless, subtle hum, a silent symphony of creation and annihilation playing out at scales so infinitesimally small they elude direct observation, yet their cumulative effect shapes the very nature of reality. The quantum world, in its very essence, is a testament to the probabilistic nature of existence. Unlike the deterministic laws that govern our macroscopic world, quantum mechanics operates on probabilities. An electron doesn't orbit a nucleus in a predictable path, rather, it exists in a cloud of probability, a region where it is more or less likely to be found. This inherent uncertainty, this fuzziness at the quantum level, is not a sign of ignorance or incomplete measurement, but a fundamental characteristic of reality itself. It suggests an underlying energetic process, a constant flux and potentiality that resolves into concrete outcomes only upon interaction or observation. This probabilistic dance hints at a deeper, more fluid energetic substratum, a sea of potential waiting to coalesce into the forms we perceive. The universe, in its most fundamental description, is less a collection of solid objects and more a dynamic interplay of probabilities, a silent, energetic conversation that gives rise to everything we can see, touch, and comprehend, and indeed, much that we cannot. Our journey into the fundamental nature of the universe has revealed a reality far more fluid and interconnected than our everyday experiences might suggest. We've glimpsed a cosmos not of static particles, but of ethereal waves and probabilities, a silent, energetic dialogue shaping existence. Now, we delve deeper into one of the most profound manifestations of this underlying dynamism: gravity. Often perceived as a simple force pulling objects together, gravity is, in truth, a far more elegant and pervasive phenomenon, a direct consequence of the very fabric of reality warping and yielding. Imagine spacetime not as an empty stage, but as a vast, flexible sheet. Massive objects, like stars and planets, are not merely sitting on this sheet, they are indenting it, creating subtle yet significant curves. These curves are what we experience as gravitational fields, a constant, subtle hum of energy woven into the very geometry of the cosmos. Albert Einstein, with his revolutionary theory of general relativity, provided us with the mathematical language to describe this cosmic dance. His famous field equations, a set of complex relationships, reveal that gravity is not an external force acting upon space-time, but rather an intrinsic property of space-time itself. They articulate a profound truth: mass and energy tell space-time how to curve, and in turn, the curvature of space-time tells mass and energy how to move. This means gravity is not static, it is a dynamic, responsive entity. Disturbances in this cosmic fabric, such as the collision of black holes, propagate outwards as ripples in space-time, known as gravitational waves, a testament to gravity's active, energetic nature. While gravity might seem insignificant when compared to the electromagnetic or nuclear forces, especially at the subatomic level where its influence is often overshadowed, its true power is revealed on the grandest scales. It is the invisible architect of the universe. This seemingly gentle curvature of space-time is the cosmic glue that holds galaxies together, preventing them from flying apart. It orchestrates the orbits of planets around stars, dictating the majestic waltz of celestial bodies. Gravity is the silent sculptor that has shaped nebulae into stars and stars into the intricate spiral arms of galaxies, forming the vast, ordered structures that populate the observable universe. From the delicate ballad of binary stars to the colossal clusters of galaxies, gravity, in its subtle yet inexorable way, governs the large-scale architecture of everything we see, a testament to the profound power residing within the subtle bending of space and time. It is an energy that, though unseen, defines the very shape and destiny of the cosmos. The universe, in its nascent moments, was a tempest of unimaginable energy, a state far removed from the serene, gravity-sculpted cosmos we observe today. Before the slow, deliberate ballad of galaxies began, before light could even traverse its nascent expanse, there was an epoch of mind-bending acceleration, a cosmic breath held, and then explosively exhaled. This was the inflationary epoch, a period where the very fabric of reality stretched at a rate that defies our everyday intuition. Imagine, if you can, a space expanding at an exponential clip, dwarfing the already staggering rate of the universe's subsequent expansion. This furious growth wasn't powered by the familiar forces of electromagnetism or the strong and weak nuclear forces. Instead, it was driven by an enigmatic ubiquitous energy, a phantom force that permeated the nascent universe, imbuing it with an outward push so potent that it smoothed out initial irregularities and set the stage for the grand cosmic structures to come. This all-encompassing, invisible impetus was intimately tied to the behavior of scalar fields. These aren't the fields we typically associate with forces, like the gravitational field that guides planets in their orbits. Scalar fields are simpler, possessing only a magnitude, a value at each point in space. During inflation, a specific type of scalar field, often referred to as the unflattened field, was believed to be in a high-energy, unstable state. As this field slowly rolled down its potential energy landscape, it released an enormous amount of energy, a process akin to a ball rolling down a hill, but on a cosmic scale and with profound implications. This release of energy was not uniform. Subtle quantum fluctuations within the inflating field, amplified by the rapid expansion, became the seeds from which all the large-scale structures of the universe would eventually grow. Think of these fluctuations as microscopic ripples on the surface of an inflating balloon. As the balloon expanded at an astonishing rate, these tiny ripples were stretched to astronomical sizes, becoming the initial density variations that gravity would later exploit. The legacy of this fiery, inflationary beginning is etched into the very bones of the universe. The remarkable homogeneity and isotropy we observe on the largest scales, the fact that the universe looks essentially the same in every direction and from every point, is a direct consequence of this rapid expansion. Inflation effectively ironed out any initial wrinkles, stretching microscopic quantum uncertainties into vast, smooth regions. Furthermore, the subtle but crucial anisotropies in the cosmic microwave background radiation, the faint afterglow of the Big Bang, are the imprinted signatures of those primordial density fluctuations. These minuscule temperature variations, on the order of parts per 100,000, are the cosmic blueprints that dictated where matter would eventually clump together, forming stars, galaxies, and the colossal clusters of galaxies that we now map. The inflationary epoch, driven by this unseen, potent energy, wasn't just a fleeting moment. It was the foundational event that dictated the universe's ultimate architecture and the very existence of the structures we inhabit and observe today. It was the universe's first, magnificent exertion, the energetic genesis of all that is. The universe, as we perceive it, is a dazzling display of light and matter, but beneath this luminous facade lies an enigma that profoundly shapes its very fabric. Observational evidence points to the existence of a pervasive, invisible substance that defies our direct detection, a substance we've termed dark matter. Its presence is most strikingly revealed in the unexpected speeds at which galaxies rotate. Stars on the outer edges of galaxies orbit far faster than they should, given the visible matter alone. This discrepancy suggests a massive, unseen halo of mass providing the additional gravitational pull to keep these celestial bodies from flying apart. Further corroboration comes from the phenomenon of gravitational lensing, where the gravity of massive objects bends the path of light. We observe light from distant galaxies being distorted and magnified by intervening, invisible concentrations of mass, precisely where dark matter is predicted to reside. The nature of these dark matter particles remains a profound mystery. we hypothesize that they are fundamentally different from the baryonic matter that constitutes stars, planets, and ourselves. Crucially, they do not interact with light, hence their invisibility. They neither emit, absorb, nor reflect electromagnetic radiation, rendering them utterly undetectable by our telescopes that rely on capturing light across the spectrum. Their existence is inferred solely through their gravitational influence. This lack of interaction with light is precisely what allows them to permeate the cosmos without betraying their presence visually. Despite their elusive nature, dark matter's gravitational influence is far from passive. It acts as the silent architect of cosmic structures. In the early universe, slight overdensities in dark matter acted as gravitational seeds, attracting ordinary matter and initiating the formation of the vast cosmic web, the intricate network of galaxy clusters and filaments that spans the universe. Without this unseen scaffolding, the galaxies and clusters we observe today would likely not have formed. Dark matter's gravitational embrace is the invisible hand that guides the ballad of galaxies, holding them together and dictating their grand, slow dance across eons. It is a testament to the universe's hidden forces, a cosmic sculptor working in the shadows, shaping the grandest designs from the unseen. For eons, the gravitational pull of matter was considered the sole architect of the universe's grand design, the invisible hand orchestrating the slow, majestic waltz of galaxies. We believed that the universe's expansion initiated by the Big Bang was gradually decelerating, its outward momentum being steadily reined in by the collective gravitational embrace of all the matter it contained. This was the prevailing wisdom, a comforting narrative of a universe slowly winding down. However, observations made in the late 20th century, particularly through the study of distant supernovae, shattered this elegant, yet incomplete picture. These celestial beacons, acting as cosmic yardsticks, revealed a startling truth: the universe wasn't slowing down, it was accelerating. The very fabric of spacetime, rather than being stretched and then constrained by gravity, was actively pushing itself apart at an ever-increasing rate. This revelation was as profound as it was perplexing, forcing a radical re-evaluation of our understanding of the cosmos. The driving force behind this unexpected acceleration was quickly attributed to a mysterious entity dubbed dark energy. Unlike dark matter, which interacts gravitationally and clumps together, dark energy appears to be a pervasive force evenly distributed throughout space. It acts as an anti-gravitational agent, exerting a negative pressure that counteracts the attractive force of matter and propels the universe outward with ever-growing vigor. Its existence is not directly observed, rather, it is inferred from its profound impact on the universe's expansion. Think of it as a silent, invisible engine, steadily increasing its output, pushing galaxies further and further apart at a pace that defies our intuitive understanding of gravity. This unseen influence is not confined to the distant reaches of the cosmos. It is woven into the very fabric of space-time, a fundamental component of the universe's current evolutionary trajectory. The simplest explanation for dark energy, and the one that aligns with current observations, is the cosmological constant, originally proposed by Albert Einstein. He introduced this concept into his equations of general relativity to allow for a static universe, a notion that was later disproven by Hubble's observations of an expanding universe. However, with the discovery of accelerated expansion, the cosmological constant has been resurrected, not as a placeholder for a static universe, but as a representation of the intrinsic energy density of empty space itself. According to this model, even seemingly empty vacuum is teeming with energy, a constant, unchanging force that drives cosmic expansion. As the universe expands, the volume of space increases, and therefore the total amount of dark energy also increases, leading to a stronger outward push. Yet, the cosmological constant is not the only proposed explanation for dark energy. While it elegantly fits the observational data, its theoretical underpinnings remain a significant puzzle. Quantum field theory predicts a vacuum energy that is vastly larger than the value observed for the cosmological constant, a discrepancy so immense it's often referred to as the cosmological constant problem. This suggests that our current understanding of quantum mechanics and gravity may be incomplete. Consequently, alternative models have emerged. One prominent candidate is quintessence, a hypothetical dynamic scalar field that permeates spacetime. Unlike the constant energy density of the cosmological constant, quintessence's energy density can vary over time and space, potentially offering a more nuanced explanation for the observed acceleration. Other theories explore modifications to gravity itself, proposing that the accelerated expansion might be a manifestation of gravity behaving differently on cosmic scales, rather than the presence of a new form of energy. The quest to understand dark energy is at the forefront of modern cosmology, pushing the boundaries of our knowledge and challenging us to rethink the fundamental nature of reality. It is the ultimate cosmic enigma, an unseen force that is actively reshaping the destiny of everything we can observe. Deep within the heart of every luminous star, a cosmic alchemy unfolds, a process so profound it paints the night sky with its brilliance. This is the realm of nuclear fusion, the engine room of the universe, where the very building blocks of matter are transmuted into pure, radiant energy. Imagine a crucible of unimaginable intensity, a place where hydrogen atoms, under the crushing embrace of gravity's relentless pull, are squeezed and heated to millions of degrees Celsius. It is in this extreme environment that their atomic nuclei, stripped of their electrons, overcome their natural repulsion and fuse together. This fusion isn't a gentle merging, it's a violent, yet orderly collision. As four hydrogen nuclei, essentially protons, combine to form a single helium nucleus, a minuscule but potent amount of mass is converted directly into energy, echoing Einstein's famous idem maceti. This is the stellar forge, constantly hammering out energy from raw atomic material. The immense pressures, millions of times greater than those found at the Earth's surface, are crucial. They act like a cosmic vice, forcing the protons close enough for the strong nuclear force, the universe's most powerful but shortest range interaction, to take hold. Without these extraordinary conditions, fusion would remain an impossible dream. The temperatures, soaring into the tens of millions of degrees, provide the kinetic energy needed for these atomic particles to move fast enough to overcome their electrostatic repulsion and initiate the fusion process. It is a delicate, yet powerful, equilibrium that sustains these celestial furnaces. And then, this incandescent energy, born from the very core of the star, embarks on an astonishing journey. It radiates outwards, a torrent of photons, through the dense stellar plasma, a process that can take hundreds of thousands of years. Once it reaches the star's surface, it streams into the vast, silent expanse of space. Traveling at the ultimate speed limit of the cosmos, the speed of light, this stellar radiation traverses unimaginable distances, crossing the light years that separate galaxies. It is this ancient light, this whisper of fusion's power, that eventually reaches our eyes, allowing us to gaze upon the distant stars and ponder the silent, energetic ballad of the universe. It's a testament to the enduring power of stellar fusion, a fundamental force that illuminates our understanding of the cosmos and fuels the grand narrative of cosmic evolution, a story written in light and heat across the timeless void. Within the vast, echoing chambers of interstellar space, where the light of distant suns only faintly penetrates, a subtler, more profound dance unfolds. It is a choreography of unseen forces, a testament to the pervasive influence of energy in its most elemental forms. Consider the interstellar clouds, those colossal, ethereal tapestries of gas and dust that drift serenely through the galactic expanse. They appear to the casual observer as placid, nebulous expanses. Yet, beneath this serene facade lies a ceaseless, intricate interplay of energies. Microscopic particles, imbued with faint electrical charges, are buffeted by the gentle but persistent solar winds emanating from nascent stars or the residual shock waves of ancient supernovae. These interactions, though individually minuscule, collectively sculpt the very fabric of these nebulae. At the heart of this cosmic ballet lies gravity, the silent, inexorable sculptor. It is not a sudden, violent force but a slow, persistent embrace. Tiny variations in density within the cloud, perhaps initiated by the passing of a stellar jet or the gravitational tug of a nearby star, create minuscule pockets of greater mass. These denser regions exert a slightly stronger pull, drawing in more of their surrounding gas and dust. This accretion is a gradual process, a cosmic gathering that can span millions of years. Imagine countless motes of dust, each a miniature world unto itself, being coaxed together by an invisible hand. Hydrogen atoms, the most abundant element in the universe, are drawn into these coalescing masses, their numbers swelling, their collective gravitational influence growing exponentially. As more matter accumulates, the pressure at the core intensifies. This relentless compression is the engine that will eventually ignite the birth of a star. But gravity does not operate in a vacuum. The interstellar medium is imbued with a complex network of magnetic fields, invisible lines of force that permeate plasma and dust. These magnetic fields act as both guides and constraints, influencing the flow of matter and the distribution of energy. They can channel ionized gas along their lines, creating intricate filamentary structures within the nebulae that are often the very pathways along which gravity draws material inward. In some instances, the magnetic pressure can even resist the inward pull of gravity, creating a delicate equilibrium that can slow or even halt the star formation process in certain regions. These magnetic fields are not static, they are dynamic, twisting and contorting as the gas within the nebula moves. Their strength and orientation dictated by the underlying plasma currents and the distribution of charged particles. They play a crucial role in shaping the nascent stars and their surrounding protoplanetary disks, influencing the eventual architecture of planetary systems. The magnetic field lines can also channel powerful outflows of material from young stars, known as jets, which can, in turn, stir up and redistribute the surrounding gas and dust, triggering further episodes of star formation in a feedback loop that perpetuates the cosmic cycle. The subtle interplay between gravity's insistent pull and the magnetic field's intricate guidance is what orchestrates the creation of these stellar nurseries, transforming diffuse clouds into the incandescent furnaces that will one day illuminate the cosmos. When stars, those colossal furnaces of atomic hearts, exhaust their nuclear fuel, a profound transformation occurs. The outward pressure that once held their immense mass in check falters, succumbing to the relentless inward crush of gravity. This gravitational collapse is not a gentle fading but a catastrophic implosion, a cosmic death rattle that compresses matter into an infinitesimally small point of infinite density, a singularity. Around this ultimate abyss, a boundary forms, a veil of no return known as the event horizon. Crossing this threshold is an irreversible descent into the unknown, a point where even light, the universe's swiftest messenger, is irrevocably captured. Yet, the story of these celestial titans does not end with their silent engulfment. A theoretical whisper, a ghostly breath known as Hawking radiation, suggests that even these ultimate prisons might not be entirely impermeable. Proposed by Stephen Hawking, this phenomenon posits that quantum fluctuations near the event horizon can lead to the creation of particle-antiparticle pairs. One particle might fall into the black hole, while its counterpart, imbued with a tiny fraction of the black hole's mass energy, escapes into the cosmos. Over unimaginable timescales, this slow leak of energy could, in theory, cause black holes to evaporate, a poignant testament to the universe's constant, albeit subtle, energy exchanges, a stark contrast to the fairy birth pangs of stars that precede their formation. It's a cosmic paradox, the ultimate consumer of energy and matter, yet a potential, albeit incredibly slow, emitter of its own essence, contributing to the vast, silent energetic tapestry of the timeless cosmos. This ethereal emission, a faint echo from the edge of oblivion, underscores the profound mysteries woven into the fabric of spacetime, hinting at deeper connections between gravity, quantum mechanics, and the very nature of existence. The cosmos, a canvas of profound silence punctuated by moments of unimaginable violence, constantly broadcasts a symphony of energetic whispers. Among these are the cosmic rays, the universe's most potent messengers, carrying tales of stellar death and cosmic rebirth across unfathomable distances. These are not gentle breezes, but torrents of pure energy, primarily atomic nuclei stripped bare of their electrons, accelerated to speeds so close to the ultimate cosmic speed limit that they are virtually indistinguishable from light itself. They are the remnants of titanic struggles, the energetic shrapnel flung outward from the most cataclysmic events known to astrophysics. Imagine a star, bloated and unstable, reaching the end of its billion-year lifespan. For many, this signifies a graceful fade into a white dwarf, a dying ember in the celestial darkness. But for the most massive stars, their demise is a spectacle of unparalleled ferocity, a supernova. As the star's core collapses under its own immense gravity, it triggers a shock wave that blasts the star's outer layers into the void at incredible velocities. It is within these incandescent explosions, these stellar cremations, that cosmic rays are born. The immense energies released, the violent acceleration of charged particles within the shock fronts, imbues them with their extraordinary power. Other prolific sources include the supermassive black holes that anchor galaxies, their accretion disks and relativistic jets acting as cosmic particle accelerators on a scale that dwarfs even supernova. Pulsars, the rapidly spinning remnants of dead stars, also contribute, their powerful magnetic fields flinging particles into the void at near light speeds. These are the cosmic forge fires, the crucibles where the universe tempers its most energetic particles. When these intrepid travelers, having traversed light years of the void, finally reach our solar system, they encounter a formidable guardian, Earth's magnetosphere. This invisible shield, generated by the molten iron core of our planet, acts as a colossal deflection system. The charged particles of cosmic rays, interacting with the Earth's magnetic field, are guided along magnetic field lines, often directed towards the polar regions. This interaction is what paints the ethereal auroras across the night sky, a breathtaking visual testament to the cosmic bombardment our planet endures. Even with this protection, a fraction of these high energy particles manage to penetrate the magnetosphere and reach our atmosphere. Here, they embark on a secondary cascade of interactions. Colliding with the nuclei of atmospheric gases, such as nitrogen and oxygen, they create a shower of secondary particles, muons, neutrinos, and other subatomic debris. These secondary particles, though less energetic than their progenitors, still reach the Earth's surface, a constant, albeit subtle, reminder of the energetic torrent that flows around and through our planet. This interaction with our atmosphere, a delicate dance between cosmic force and terrestrial defense, highlights the intricate, interconnected nature of our place within the grand cosmic theater. It is a testament to the resilience of life on Earth, shielded by forces both within and without, yet forever touched by the echoes of distant, violent celestial events. Beyond the tangible grasp of touch and the audible resonance of sound, a universe of information is constantly being broadcast, an intricate tapestry woven from silent energy. This is the realm of the electromagnetic spectrum, a vast and varied continuum that stretches from the languid, expansive wavelengths of radio waves, capable of traversing unimaginable distances, to the frenetic, powerful bursts of gamma rays, born from the most cataclysmic events in the cosmos. Each segment of this spectrum, from the gentle warmth of infrared to the energetic sting of ultraviolet, acts as a unique messenger, carrying within its oscillations the stories of celestial bodies and phenomena that would otherwise remain forever veiled. Light, in its myriad forms, is the primary conduit of this silent communication. It is not merely illumination, it is a coded dispatch from the past, a snapshot of distant stars, nebulae, and galaxies at the precise moment the light was emitted. When a star ignites, when a supernova explodes, or when a galaxy merges, these events send ripples across the electromagnetic spectrum, painting a picture of their nature, composition, and evolution. These ethereal messengers, traveling at the universe's ultimate speed limit, carry the spectral fingerprints of elements, the telltale signatures of temperature, and the profound evidence of motion, allowing us to peer back in time and witness the universe's grand unfolding. Astronomers, armed with an array of sophisticated instruments, have become adept at deciphering this cosmic language. Telescopes, from the ground, based behemoths that capture the faintest radio whispers to the orbiting observatories that, unfettered by Earth's atmosphere, embrace the full spectrum, are our translators. They are designed to capture, differentiate, and analyze these invisible waves, transforming them into data that can be visualized and understood. By dissecting the light, scientists can determine the chemical makeup of distant stars, the velocity at which galaxies are receding, the presence of exoplanets orbiting alien suns, and even the faint afterglow of the Big Bang itself. This ongoing process of detection and interpretation is akin to piecing together an infinitely complex, luminous library, where each photon is a word, each spectrum a sentence, and the entire electromagnetic universe a chronicle of existence, waiting to be read. It is a continuous dialogue with the cosmos, conducted in a language of pure, silent energy. The universe, as we perceive it through the vibrant spectacle of light, is only a fraction of its true narrative. Beyond the dazzling dance of photons, A subtler, more pervasive form of silent energy threads its way through the cosmos, carrying secrets from the most violent and ancient of events. These are the neutrinos, ethereal messengers born in the fiery heart of stars, and the cataclysmic death throes of supernovae. Unlike the photons that paint our skies with color and form, neutrinos are elusive, almost impossibly so. They possess an infinitesimal mass, so close to zero that for a long time they were thought to be massless altogether. This near weightlessness, combined with their profound lack of electrical charge, renders them almost invisible to the universe's pervasive forces. They do not scatter off electrons, nor are they bound by the electromagnetic tug of war that dictates the fate of most matter. Instead, they engage in a solitary, almost defiant existence, interacting with the universe through the weakest of the fundamental forces, the weak nuclear force. This interaction is so infrequent, so fleeting, that a neutrino can traverse entire light, years of solid matter, the dense core of a star, the crushing embrace of a planet, without leaving so much as a ripple in its wake. Imagine a ghost passing through a solid wall, not by phasing, but by simply being so utterly disconnected from the material world that the wall itself offers no resistance. This is the neutrino's gift and its enigma. The genesis of these cosmic whispers lies in the very furnaces that ignite the stars. Within the incandescent cores of stellar bodies, nuclear fusion, the process that powers them, is a constant cascade of transformations. Protons collide and merge, forging heavier elements, and in these violent alchemical reactions, a handful of neutrinos are inevitably born. They are the byproducts of processes that create light, yet they themselves are invisible to our eyes, a silent testament to the immense energies at play. But it is in the spectacular demise of massive stars, in the cataclysmic event known as a supernova, that the universe unleashes its most prolific neutrino storms. When a star collapses under its own immense gravity, the resulting implosion is a crucible of unimaginable forces. In the heart of this collapsing inferno, the sheer density and energy are so profound that they rip apart protons and electrons, creating an overwhelming torrent of neutrinos. These neutrinos, numbering in the trillions of trillions, erupt outwards, carrying with them an imprint of the star's final moments, a snapshot of the ultimate nuclear ballot. They are the immediate aftermath of a cosmic explosion, the first silent heralds of a transformed stellar remnant. For an observer on Earth, shielded by our atmosphere and magnetic field, the journey of a neutrino is a humbling reminder of the universe's hidden dynamism. While photons from distant galaxies are absorbed, scattered, and distorted by intervening matter, neutrinos plow through, largely undisturbed. They are the ultimate cosmic archaeologists, carrying direct evidence from the heart of stellar processes that are otherwise inaccessible. Detecting these elusive particles is a monumental feat of scientific ingenuity. Large, subterranean detectors, often shielded by miles of rock or water, are designed to catch the infinitesimally rare instances when a neutrino does deign to interact with matter. These interactions, though improbable, create tiny flashes of light or electrical signals, allowing scientists to reconstruct the neutrino's trajectory and infer the nature of its origin. Each detected neutrino is a victory, a fragment of information wrested from the universe's silent depths. They offer a direct window into the nuclear reactions within stars, allowing us to test our models of stellar evolution and the fundamental laws of physics under extreme conditions. They are the universe's secret correspondence, delivered without fanfare, yet holding the potential to rewrite our understanding of existence itself, much like uncovering forgotten texts in a boundless, luminous library, each silent particle a key to unlocking deeper cosmic chronicles. Our universe, a breathtaking tapestry of stars and nebulae, owes its very structure to forces and substances we cannot directly perceive. The celestial ballad of galaxies, vast congregations of billions of stars, is orchestrated by an unseen hand, the collective gravitational pull that binds them into cohesive, spinning entities. This immense, unifying force is not merely the sum of visible matter, rather it is profoundly influenced by the enigmatic presence of dark matter. These invisible scaffolds, known as dark matter halos, envelop galaxies, providing the gravitational anchor that prevents them from disintegrating under their own furious rotation. Without these halos, the stars, gas, and dust that constitute a galaxy would likely scatter into the cosmic void, leaving behind only ephemeral wisps of what once was. The relationship between the visible and invisible components of a galaxy is a testament to a dynamic, intricate interplay. Stars born from swirling clouds of gas and dust ignite in brilliant bursts of fusion, their light illuminating the galactic disk. Yet, much of a galaxy's mass, and crucially, its gravitational stability, resides in the diffuse, undetectable realm of dark matter. This unseen substance permeates the galactic halo, its gravitational influence extending far beyond the luminous boundaries of the visible stars and gas. It is this silent, pervasive gravity that dictates the orbits of stars and gas clouds, shaping the very morphology of galaxies, from grand spiral arms to the more monolithic forms of elliptical galaxies. The journey of a neutrino, as we've glimpsed, is but one thread in this grand cosmic design. Understanding these invisible architects, the dark matter halos and the gravitational architecture they provide, is paramount to comprehending the enduring stability and evolution of the cosmic structures that populate our timeless universe. It is through deciphering these silent gravitational whispers that we truly begin to grasp the profound elegance and hidden mechanisms that govern the cosmos on its grandest scales. The universe, as we observe it, is not a random scattering of celestial bodies but rather an intricate, vast network of galaxies, a breathtaking cosmic web. Imagine colossal, luminous knots of stars and gas, the galaxies interconnected by impossibly long, filamentary strands. These aren't physical bridges of matter, but rather vast, diffuse streams of dark matter, the invisible scaffolding upon which the visible universe is built. This grand architecture, stretching across billions of light years, is a testament to the subtle yet powerful forces that have shaped the cosmos since its inception. At the heart of this cosmic lacework lies the pervasive influence of gravity. It's the invisible hand that drew matter together in the early universe, coalescing primordial gas clouds into the first stars and galaxies. Over aeons, gravity continued its relentless work, pulling these nascent structures into the intricate web we see today. Galaxies are not isolated entities. They are bound together by the gravitational pull of the invisible dark matter that forms these vast filaments. Without this unseen framework, the universe would likely be a far more homogeneous, less organized expanse. The distribution of galaxies is not uniform, it's clustered and filamentary, mirroring the underlying distribution of dark matter. These regions of higher density, the knots in the cosmic web, are where galaxies are most abundant, forming clusters and superclusters. The voids between these filaments are vast, near-empty expanses, highlighting the web-like nature of cosmic organization. However, this elegant gravitational structure is not static, it is in a constant state of evolution, and a mysterious force known as dark energy plays a pivotal role in this ongoing transformation. While gravity has a tendency to pull matter together, counteracting this cosmic clumping, dark energy acts in opposition. It is an enigmatic, pervasive energy that permeates all of space, exerting a negative pressure that drives an accelerated expansion of the universe. This expansion is not merely pushing galaxies apart, it is actively stretching the very fabric of spacetime, causing the cosmic web itself to grow larger and more diffuse. The implications of dark energy are profound for the large-scale structure of the universe. As the universe expands at an ever-increasing rate, the filaments of the cosmic web are being stretched thinner, and the distances between galaxy clusters are growing. In the distant future, this accelerated expansion could lead to a scenario where galaxies beyond our local group become causally disconnected, their light forever lost to our view as the space between us and them expands faster than the speed of light. Dark energy, therefore, acts as a cosmic accelerator, influencing the rate at which new structures can form and the ultimate fate of the existing cosmic web. It is the silent, unseen force that dictates the grand narrative of cosmic evolution, subtly altering the dance of galaxies and the very geometry of the universe. Understanding dark energy is key to understanding how this grand tapestry will continue to unravel and reconfigure over the unfathomable timescales of cosmic history. Its influence is subtle yet inescapable, shaping the past, present, and future of the universe's most expansive structures. The cosmos, a vast expanse of silent, unfolding grandeur, continues to hold its deepest secrets close. While we marvel at the visible ballad of stars and galaxies, a profound mystery persists in the unseen currents that govern its very existence. Current scientific endeavors are relentlessly probing the enigmatic nature of dark matter and dark energy, those invisible forces that collectively dwarf the familiar matter and energy of our everyday experience. These investigations are not merely academic exercises, they represent a fundamental quest to decipher the universe's underlying architecture. Researchers are meticulously analyzing subtle gravitational distortions, mapping the large-scale distribution of matter, and observing the accelerating expansion of space itself, all in an effort to grasp the essence of these elusive components. The implications of these studies extend far beyond cataloging cosmic constituents. They are intrinsically linked to the search for new physics that lies beyond the current limitations of the Standard Model. The Standard Model, while remarkably successful in describing the known fundamental particles and forces, offers no satisfactory explanation for the existence or behavior of dark matter and dark energy. Therefore, the ongoing research into these cosmic enigmas acts as a powerful catalyst, driving theoretical physicists and experimentalists alike to explore radical new ideas, from hypothetical particles and fields to entirely novel interactions that could reshape our understanding of reality. This pursuit of physics beyond the Standard Model is crucial not only for explaining what we observe, but also for predicting what we cannot yet see. Furthermore, these investigations are inextricably tied to the ultimate question of the universe's fate and its grand energetic destiny. Will the accelerating expansion driven by dark energy continue indefinitely, leading to a cold, dispersed universe where all structures eventually fade into oblivion? Or are there other, as yet undiscovered, energetic forces at play that could alter this trajectory, perhaps leading to a reversal or a cyclical existence? Understanding the precise nature and evolution of dark energy is paramount to constructing accurate cosmological models that can forecast the universe's long-term future. The quest to comprehend these unseen energies is, in essence, a quest to understand the ultimate narrative of our universe, from its nascent beginnings to its eventual, perhaps unimaginable, conclusion. Each discovery, each refined measurement, brings us a step closer to illuminating the energetic horizon that defines our cosmic home.